Okay, are we all good to go, or does anyone need a minute?
I'm good.
Cool. Okay, so for like the very basics, the binary exploitation, one of the most common exploits is a buffer overflow, and buffers and the stack can be a bit of a hard concept to grasp at first, so I think doing an Excel is probably one of the best ways to describe it. So a stack is basically a temporary memory space where program data can be stored during execution, and there are a few different things that are stored on the stack. So one of the things at the bottom is going to be a return address, which basically means when the function finishes executing, this is the address that it goes back to. And for anyone who hasn't looked into stacks much before, it's basically a last in first out system, which means, so if I have like 5 numbers here, 1, 2, 3, 4, 5, and then I want to put something in the stack here. So say this is the bottom of the stack. If I wanted to add 1 in, I'd do 1 here, and then take 1 out from that. And then if I wanted to put 3 in, 3 would go above 1. And then the only way to get back to 1 is by taking out 3 first. This is called like popping items off the top of the stack. So you need
basically a can of Pringles.
Yeah, pretty much. Like, you put the Pringles in, you have to take the Pringle out at the top first. So you take out 3 first, and then you can get to 1. So, say we have like, some different addresses on here. If I want to get back down to the return address, I need nothing else on top of it first. So that's how a stack works. So stacks in actual programs just store data on them, and then you can push things to the stack, which puts it on the top, and then you can pop them, which takes it off the top. So one of the things near the bottom of the stack is the return address, and then we have ESP, which is the saved pointer. You don't really need to worry about that. And then on top of this is all the variables that are local to a function. So say we had a function that is just like something like this. It's kind of stupid to write this in Excel. I'm gonna get Notepad open. There we go. So say we had a function like this, and then we had like an int called var. So that would be stored here. But it wouldn't actually be the value var. It would just be the data it's holding. So it would just be the number 1. And then if we had like a string called test, and then it had the data word in it or something like that, then again, like on top of that would be word. So the way buffer overflows work is in at least like C, like when you're actually writing stuff like C, when you write stuff into a string, or like when you store a string, you usually create a buffer first. So you do char start, or when you define strings in C, you usually write the length of the string. So you would do like char test, and then in brackets you do the length, so say 16. So then that would allocate 16 bytes on the stack. So say each of these holds 8 bytes, it would say that these 2 blocks are allocated specifically for this variable. So these are allocated to the test variable. And then if you had another buffer on top of it, so you had test2 with another 16, then these 2 would be allocated to test2. So that's all fine, and usually when you create safe code, what you do is you limit the amount of characters that you can write into a buffer. But what causes a buffer overflow is when you use specific functions or ways of inserting data that aren't safe. So say you use the function get, this basically gets data from a source and writes it into the buffer. Say that you wrote something into gets, like with Ahmed's program. So over demo, it gets this argument to the program, so it'd just be Q in this case. But you can see that if we write a load of characters in here, it says segmentation fault, which basically means that a buffer overflows happen. So we can see what's happened here is like it's read the first 16 bytes of hit and it's written it into the buffer as it should. But then it reads all of the data past this as well, and instead of storing it safely, so say the data in test 2 was like Qs, right? So say we got 4 Qs here, so do 8 for each one here. So these are stored normally. 8 Qs. So those are stored correctly, but then all of the Qs after that are going to start overwriting other data on the stack. So then it'll overwrite the first test value, so that'll get overwritten. And then you overwrite ESP with Qs, and you overwrite the return address as well. Now, it can be kind of hard to understand why this is like a bad thing. Obviously, if there's a program that's like, if you have like an int here that you want to overwrite, so if it's like an auth check, or something like that. This actually needs to be on top, so it gets put below. So auth check. If this is set to 0, and then to log in you need it to be set to 1. If you overflowed this, and then you did something like a load of Qs and then a 1 at the end, then you could line it up perfectly, so it writes the Qs, and then it writes the 1 in here, and then when it returns, it will think that it's been written legitimately when it hasn't. So that's one way of doing it. But when you don't have something like an auth check, what you want to be doing is overwriting the return address. This is really powerful because you can basically tell the program to continue at any point you want in memory. So there's, if you haven't used registers before, it's basically how CPUs store data. So there's like a few registers, so there's like some general purpose ones like EAX, EBX, ECX. These just hold any kind of data. And then you have EIP, which is the important one here. This is the instruction pointer, so this basically defines that the next instruction that will be read. So when we control the return address, we basically control EIP, so we can tell it where to read. So what we do with this, by default, we don't really have anywhere useful to read in memory. There are some functions you can go to, so like there's the system function in C programs that can launch programs, but instead of doing that, we can actually just use our own code to get it to do what we want. So this is what shellcode is. So shellcode is basically just raw assembler instructions, so it's doing this. Like it's going through line by line doing these instructions, and these text instructions correspond to these machine code values. So whoever was in year 1 here, we had like the systems and networking module where we'd had like the instruction set, and the numbers corresponded to values on the instruction set. So it's just the same thing here. So shellcode, like this is just raw bytes, but it corresponds to these like assembler instructions. So when you have something like this, this whole shellcode basically sets up to spawn a shell on the host machine. So it doesn't really matter what it's doing exactly, but it's basically just setting up the registers in a way that when it does this, int oxap, it's going to spawn a new process of bin bash or bin sh or whatever shell. So if we can somehow get this to run, then we can spawn a shell on the machine. So that's why controlling the return address is so important, because if we can get the return address controlled, and then we point the return address to our shellcode, then it'll start executing that and it'll spawn a shell. So the way we actually do that is we can go into GDB, and GDB is just a debugger which allows you to kind of control a program, and you can stop it at certain points in memory, you can create breakpoints, you can do a lot of stuff with it. It's very powerful, but it's kind of hard to learn at first. But we don't need to do too many complex things with it. So one thing you can do is create a pattern with patta, and then just, you can say 100 bytes. we only use this because it's an attribute or an argument that we need to use. Otherwise, we just use something like pattern create to put it into a file and then load that in. But for this, it sets the attribute or the argument of the program as a pattern. So then when we actually run this, again, we get all of this like huge block of data, which looks really scary, but it's actually just telling us basically what's in the registers at that moment when the program crashed, and what's in the stack. So we can see like what has happened here. So these values in the stack. So the stack grows from the bottom up, so these would have been written first, and then these. But our pattern has basically overwritten everything on the stack, and also like everything in a lot of the registers. So if we type pattern search, then we can see what specific offsets we need to use to overwrite certain registers. Because if you can imagine, like, if we write 8 bytes, then we're going to overwrite this block. If we write 16, we're going to overwrite that block and this block, and as it goes on, 24, 32. So in this case, if we overwrite 16, then we start writing it into EAX. If we overwrite 24, we start writing into EBX. But the important thing here is we can see we overwrite EIP at offset 32. So that means if we write 32 bytes, then the next 4 bytes after that, because memory addresses are 4 bytes in a 32-bit program, so the next 4 bytes after that are going to be the memory address that EIP is going to point to. And then we can start writing our exploit knowing this. So I just do it in Python usually, but you can use any language really. So again, so we know the 32 is the length we need to reach before we start writing into it. So what we do is just create some padding. So this can be literally anything. You just do 32 A's, and then at the end we can print out the. So if we just do padding for now. So if we do python exploit.py, we just print 32 A's. So then whatever we add after this padding is going to be our shellcode address. So if we make a variable called shellcode address, and then we set that to, so for now we can just set it to something like, if we just set it to AAA, or let's set it to BBB to differentiate, shellcode address. So then when we run that, it's going to have 32 A's and then 4 B's. And then when we actually run that in here, so we can see that EIP is pointing to BBBB, and this is just a hex representation of that. So now we know we can control where it's pointing to. What we actually want to do is find where the shellcode is stored, and then we want to point it there. Well, we haven't inserted shellcode yet, but we want to insert the shellcode, look at where it's stored, and then point EIP there. So now we can grab the actual shellcode. So we just take from here, copy paste this. It's formatted kind of annoyingly. There we go. So we've got our shellcode there, and then we can add the shellcode at the end. So what it's doing is just printing the padding, then the shellcode address, and then the shellcode itself. So when we run that again, we can see like it's a load of garbled bytes, but you can kind of see some things in here. So we have like bin sh in here, which is the shell we're trying to spawn. We can also pipe this into xxd and just read the bytes directly. So we can see the first 2 lines here are filled with A's, and then we have the return address here. And then everything after this is just the shellcode. So now that we have that, we can run this again, and we can see our shellcode actually in the stack. So yeah, we can see if we look at the first bytes of the shellcode, so we've got 3, 1, and C0. Because we're storing a little endian, it's going to represent it backwards, so we've got 3, 1, and C0 here. And we can actually see the memory address for this here, which is really useful because that's exactly what we need. So what we do with that is just replace our shellcode address with the address of the stack here. So again, we'll write it backwards because of little endian. So we do E0, CF, FF, FF. So now the shellcode address is going to point here, which is where our shellcode starts. And then it's going to read these bytes and start executing them as if they're instructions. So now hopefully when we run this, yep, so we've got a shell now. It won't work entirely correctly in GDB because it forks off a different process, but we can see if we use ls, then we can see the ls output here. Another good way to show this, and again, we can use GDB for this. If we do disas main, it will disassemble the main function. It's actually good to break main because it hasn't loaded into memory yet, so these memory addresses aren't going to be correct. But first we do break main, which is just going to set a breakpoint as soon as the program starts. And then we run. And then we can do disas main, and these are the correct memory addresses now. So we can see here this check authentication function is being called. So we can disassemble this as well. And there is an easier way to do this. I don't usually read code in GDB. I use something called Gidra instead, which I can just show quickly. It's a really nice tool. It's made by the NSA as well, so you can feel like a real hacker when you're using it. Just takes a minute to boot up. There we go. And I think I have it open already. Yep. So what Gidra will do is just, it will load this in, and then it's a decompiler, so it makes it a lot easier to read the code. So it'll just analyze this code, it'll recognize all of the functions, and then we can go here on the left, look at the main function, and we actually get, like, this is a million times easier to read because it just converts it to C for us. It's really ugly C, and it doesn't always convert it properly, but it's still way easier to read than actual assembly. So we can kind of understand what's going on here. So param1 is argc. And if you've done any programming in C before, you know that argc and argv are the two. Is it char***? Yeah. So these are the two arguments that you use to read, or the two properties that you use to read arguments from the command line. So what this does is looks at argc, and if there's no second command or no second argument, then it will exit. And then if there is one, then it will run the check authentication function with the first argument. So now inside check authentication, we can see, so these are the actual passwords that I use. If you type these in, so if we just run over demo, and then we type in USN, it will give us access granted, as opposed to anything else, it gives us access denied. But that's not really relevant to this, it's just like interesting to see some of the code. But this is where we can see the actual vulnerabilities. So this is the user input. So this defines a buffer of 16 bytes, and then this uses string copy with argv. So this inserts the argument directly into the buffer without checking its length, which is why we get the buffer overflow. And then when we actually start executing code, it's down here where the return instruction is. So what we can do here is get the actual start address for the binary. So that's right here. If you type vmmap in GDB, you get that. And then we can go up here and change the home because it doesn't read it by default. So once we've done this, all the memory addresses will be aligned correctly, I think. Yes. Okay. So then we can see the actual return address here. So then if we grab the return instruction, copy that, and let me set a breakpoint in here. Now when we run this with the exploit, so I guess it just breaks at main, and then it breaks at the return instruction. So we can see we're at this point in the code, and the return instruction basically says get the top address on the stack and then jump to that. So we can see on the stack here the address we've got is this one, which is the address of our shellcode. So we should start jumping straight into our shellcode. So I'm going to single step forward, which basically just takes it one instruction at a time. So we can see here, it's done it correctly. As we can see, if we look at the shellcode in here, the first instruction is XOR EAX with EAX, and that's the same one here. So now we can keep single stepping through, see what it's doing. So it's executing all the instructions as we expect, and then it gets to int x80, and it executes the program. So that's how it actually steps through and goes through the parent function and then returns into our shellcode. So that works inside GDB, but if we exit now and we try that with the actual binary, then this doesn't work. We got a segmentation fault because so when we're in GDB, there's certain environment variables. These are a thing in Linux and Windows, I think, but you don't usually interact with them that much. But if we do, and we can see all the environment variables here. So these will be slightly different when we run it in GDB compared to when we run it outside of GDB. And that's an issue because those environment variables are stored at the top of the stack. So when they change length, it slightly changes the memory addresses that we need. But it's not a big deal because we've got this core file, which is basically a memory dump of the program when it crashed. So we can use GDB for this as well. So if we go over demo core, so we can see here the core was generated by this, which is just our program, and then the shellcode we used, and it says where it's crashed. So we can use this and use GDB to read memory. So this is the syntax used to read memory in GDB. It's basically just saying read 100 memory values from here. So x/100x. You can use some other stuff as well. This will do like 100 strings. It just shows the data in different formats. So now if we do this, we can see a memory dump of that general memory address. So we can start to recognize, well, what we're looking for here is our shellcode, right? Because we want to jump into that and start executing. And it can be kind of hard to spot at first, but we can start looking for things that we recognize. So we know that 4-1 is A in ASCII, so we can make a pretty confident guess that this huge block of 4 1s is going to be equivalent to this input. So if we look at this, we should be able to guess that this is our return address, which it is, as we can see in the exploit code. So this was our shellcode address. And then after this is where our shellcode actually starts. So we can see the memory address of this on the left, so it's D010. So if we just change this to D010, exit back out, then hopefully when we run this again, we've got our shell. So that's all lined up correctly, works inside and outside of GDB. Again, it's a bit more annoying. You don't usually get these issues with the alignment. It's only because of it uses an argument instead of reading in the text from the program itself. But you know how to solve that now as well using core. And yeah, that's basically how you solve the challenge. There's a few other issues you can run into. Sometimes certain shellcode will work and others won't, so you kind of have to play around with it a bit. Sometimes you have to play around with putting the shellcode before or after the address. It's just things like that, and there's no real like easy way to learn it apart from just doing it and getting stuck and getting someone to help you and then learning where the pitfalls are. I'm also aware this is like a massive amount of information intake at once. I've recorded it, so you can just watch this back afterwards if you want to see individual steps. But yeah, if anyone has any questions about how this works or if there's anything confusing about it, then feel free to ask.
I just want to say that it was very well explained, and I understood way more now than when you showed it briefly on Ahmed's stream. So
yeah,
thanks.
I was having to debug at the same time as explaining it then, so I was like panicking because it's very difficult to figure out what's wrong while also trying to explain how it works. But yeah, it's going through like how the stack works and everything first. I think it makes the understanding process a lot easier. Like being able to visualize how you're overwriting data, it made it a lot easier to understand for me at least.
Yeah, it's very, very cool. How long have you known how to do this? I can see that you've used the programs many times.
Mm-hmm.
So I understand what you are doing, but I don't know the programs. So I'm just wondering how long did it take you to learn the different programs and such?
Yeah, I started binary exploitation in a CTF around Christmas last year, and then I've done a few CTFs since then, and there are a few hack the box boxes that have stuff like this around. But yeah, it is something that can take a bit to pick up, but it's pretty interesting for me at least. Like it depends on like if you find it interesting or not, but it's something that can be cool to play around with. And there's like this is just the beginning as well. Like this is stack based stuff, but then there's if we look at so we can use something called checksec for seeing which protections the binary has on it. So this is actually like a fully unprotected binary, and when you get into more advanced stuff, you start figuring out how to bypass things. So we can see NX is disabled here. There's no stack canary, and has read-write segments. So yeah, the more you go into it, the more protections you learn how to bypass, and there's different things you can do jumping around using functions that are already in there, stuff like that. There's a lot of interesting stuff, but yeah, it's a bit daunting to pick up at first.
Yeah, for sure. It seems like a cool and deep rabbit hole to dive into, to be fair.
Yeah, definitely. Does anyone else got any questions on how stuff works specifically, or like any concepts you want to know more about? Or... I feel like a lecturer now, just like asking questions and
And no one answered.
I guess it was cool, even though for us in second year it's quite complex to understand what's going on fully. Got the main concept, I think.
Yeah, and there's a lot of resources that you can like look up as well. So yeah, like Live Overflow is a guy that has a big playlist on how stuff like this works. So yeah, when I was first starting, I basically just watched this whole playlist.
Alright.
And he goes through like the very basics up until the more advanced stuff. Yeah, it's like 57 videos. I think the first like 20 or so are definitely worth watching. But yeah, it is good. It is kind of like something that seems kind of useless at first because you don't usually come into contact with like binaries, like raw binaries that you have to work with. But actually, like a lot of the concepts transfer between different things. Like I understand C and C++ way more now after doing stuff like this because it's a lot easier to visualize how stuff like pointers work.
Cheers, Will. It was really good.
Yeah, no problem.
Did you ever work out why the shellcode wasn't working with the other one that we used?
Yeah, I have no idea. So yeah, we did this before. Me and Toby were trying to debug his yesterday for ages, and yeah, for some reason there was another shellcode that was this one, I think, that like even when I used it today, it was stepping through all the instructions correctly, but then when it reached this one, it would just like change the instructions afterwards out of nowhere. Like some data would get corrupted, and I have no idea why. So it is like one of those things where it's not like Python or whatever where you get like a nice pretty error message telling you what's wrong. Like the best you're gonna get from this is like segmentation fault core dumped, and then it's like, yeah, have fun with that. So it is kind of tricky because even if you're like 1 byte off or whatever, it can ruin the entire program, and you have no idea why. But yeah, you get comfortable enough with it to figure out where the pitfalls are.
Yeah, I think learn how to use GDB and able to learn how to like you just did then, where you dump the values in the registers with that X100 thing. As soon as you know stuff like that, you can start to like trace back the steps that are causing the issue.
Yeah, definitely.
But I think at first, like especially even if you haven't got PEDA installed,
Oh yeah,
GDB
yeah, get PEDA.
is so horrible to use.
I'll link that in the Discord as well because
Sure.
it's super
Because
important.
without that, like I don't know, I think I probably would have slammed my head through the wall last night.
Yeah, PED is an extension for GDB that makes it way easier to use and gives it more functionality. So I definitely recommend getting that.
You run it without it, it's literally just giving you like white lines, like one line of like broke.
Oh, I also forgot to mention ASLR. So yeah, ASLR is a protection that's installed on most modern operating systems. Basically what it does, it kind of randomizes the addresses of the program every time you launch it. So you need to disable that if you're going to be doing stuff like this. So there's a command to do it. So yeah, it's just this one. So this will just turn ASLR off and it won't mess with your memory addresses when you're trying to execute your shellcode. I don't know if there's like an example I can show you if I made like a quick C program. It's going to be tough because I'm still
I mean, you
creating
could
a reg in C.
run admeds with and then capture it with it on, and then capture it with it off.
Yeah, but I can also just do if I like define a pointer or something. How do I even test? I don't remember what library printf is in. Wait, God, I hate C. I mean, I like C, but I hate it as well.
The first years that you say that after you're going to be their teacher.
Yeah, I know, right? Standard IO, there we go. Printf. So if we define like int test equals 1. Printf test. I think that's how you do it. That just shows the pointer, I think. GCC test. Let's see.
Good.
Oh wait, I need to. Oh wait, yeah. Undefined reference to main. Oh wait, whoops. I think I need to do this. Maybe before. Yeah, I do not work with pointers in C at all. Is this how you do it? I have no idea. looks good. This is the real way you program. Writing your own code is for idiots. Okay, never mind, this guy's code sucks.
It's a real like whirlwind of emotion I feel for you right now.
Yeah, I know, right? There we go, okay. So yeah, ASLR is off, so we can see the address is the same every time. But if I turn ASLR on, there we go, it randomizes every time. So yeah, that's the thing that was stopping your shellcode from working, Toby, because it was just like setting a different address every time.
Yeah, I mean that.